So this is a very quick abridged version of the notes that I'm going to tape here. And what we're looking at is atomic history. We just want to have an understanding of how we know this information about a particle that is so itty bitty we can't see it. So how do we know all these things about protons, neutrons, electrons? And you have notes that are all pretty well described, so that's why this is an abridged version. But first of all, Democritus, he was not a scientist. He just sat on a rock, scratched his head, and he thought about things, and he said, hey, I bet all this stuff out there is composed of these small particles that can't be divided any further. And he termed those atoms. And then Dalton came along. What you should see from here is he had four tenets to his idea, his atomic theory. He did some work with gases. And basically, there are two of them. I'm going to let you read through these, but there are two of them that have since then had to be revised. And those are the ideas that elements are composed of atoms that cannot be further broken down. That's how he believed it, but we now know about subatomic particles. And then the second one that had to be later revised was the fact that he said all atoms of a given element weigh the same. Those of different elements weigh different amounts. And we have since discovered that that's not true because of isotopes. So we know that an atom of carbon and another atom of carbon are not necessarily the same. You can have carbon 12, carbon 13, carbon 14, etc. Okay, and so from this information, he was also able to use the data, excuse me, and come up with some molecular formulas, some things like that. He could look at the ratios and figure out things like there's 2 parts hydrogen to every 1 part oxygen. Okay, this is just a visual for isotopes there. And then J.J. Thomson came along in 1897. He did some work with a cathode ray tube. Basically, there's a vacuum, and you've got this gas inside of here, and this beam, which this didn't matter what the gas was. He could always get this beam created. He had this fluorescent material where he could measure the deflections of this beam. Didn't matter what gas he had inside of this tube. He could get it to deflect varying amounts, but he could get it to deflect by putting some charged plates on each side. Now, if this were just a regular beam of light from a flashlight or something like that, that would not occur. So what that means is there's got to be something else inside of this, and he determined that it would have to be negative particles. And we can see that because this beam is being deflected towards the positive, so obviously that means that there's some negatives in there. And here is a list of some things that would affect the deflection. So if it was a different gas, yeah, it might deflect a different amount because of the mass of that gas would be different. But there were some things that changed how much it was deflected. But regardless, it always deflected. And he was able to use those differences and come up with some calculations to determine the mass to charge ratio for these particles, which he knew were negative. And what he saw was that they were always the same. It didn't matter what gas he used or what metals he used for the cathode and anode. So based on this information, he said, hey, all of these things have identical negatively charged particles in them. And he came up with the term of electrons. And we talk about the plum pudding model, which is shown right here. Plum pudding, I guess, was the dessert of the day in Britain at the time. And basically, he just said, yeah, there's this random, these are the plums, this random scattering of these negative particles in here. And yeah, there's probably got to be some positives in that pudding stuff as well. So Millikan had a pretty cool experiment. He set up this chamber where he was able to have this oil and an atomizer. In other words, he got a really, really, really fine mist of these oil particles, and the electrons, negative charges, were attracted to these oil droplets. So you get anywhere from 1 electron to a whole bunch of electrons on each of these oil droplets. Well, he did this experiment thousands and thousands of times. Meanwhile, he set up this viewer right here where he could determine what was going on. So it was a magnifier. So we see that these oil droplets that have electrons attached to them, they would fall due to gravity through this tiny little hole in this plate. And what he could do is he could view it and suspend that oil drop right there in the middle by adjusting the charges on those 2 plates. So this, I can't really see this, I think that's positive and this one's negative. But he would adjust the charges on these 2 plates and get this drop to suspend right there. Again, he did this thousands of times, and he showed that the electron has the smallest possible negative charge. So every time he did this, he got whole number multiples of that small number negative charge. So he was able to go ahead and calculate the mass of an electron as well. When he did that with, I kind of skipped ahead. He figured out the charge of an electron. Then he also was able to combine it with Thomson's work, which, remember, Thomson figured out the mass to charge ratio. So if he knows the charge and he knows the mass to charge ratio, he could determine the mass of an electron. And then another really cool experiment, Rutherford, what he did was he knew that this was still kind of the common idea of what the model of an atom looked like at this point, our plum pudding model. And remember, Millikan just added to that by knowing the charge and the mass of those electrons. And what he wanted to do, Rutherford wanted to show that the atom was mostly empty space. And so his experiment, he got this gold foil, and he got the thinnest piece of gold foil that he could come up with. Ideally, what he was wanting was just one layer of atoms, which of course would be somewhat impossible. But he got a very thin layer of gold. And then he got a radioactive source, put it in this lead box, and with a slit here and a slit here that allowed just this tiny little pathway of alpha particles to be emitted. And the important thing here about alpha particles is that they are positively charged. So these alpha particles were emitted and shot at the gold foil. And then he set up this scintillation screen in the back, and what that did was detected where those alpha particles landed. And yes, just like he thought, most of the atom is empty space, because most of it went straight through with some minor deflection. But what really threw him is the fact that occasionally he would get great deals of deflection, and it would almost bounce back at him. So here's a closer up view of it. Again, most went straight through. It was these particles that perplexed him or really startled him. He did not expect that. So of course what that shows is that, again, we've got our expected and observed results. What that shows is that, yes, most of the atom is empty space, just like he thought, and the atom has a really dense, really tiny, positively charged core. So that's what he found out from that. And based on the number of times that it hit in the back and where it was deflected, he could go through and do some calculations also about the diameter of the nucleus compared to the diameter of the atom. So knowing that it was really tiny and really dense, and that's where the positive of that atom was contained. And then finally he said that the electrons must be outside of that nucleus. They whirl around somewhere. So that is it for the notes from today. There's more information about scientists on there, and we will address those another day.